So good morning. I will talk about anomalies in Brownian motion, a work I've been doing with Mary Suñe. So first of all, let's show a typical trajectory that a meso-sized particle in a simple solvent takes. So it's a kind of erratic motion that it's the Brownian motion. And this erratic movement is due to the collisions that take place between this meso-sized particle and the particles, the molecules of the solvent. To have an idea about the length scales we are talking about, it's about a few hundreds of nanometers, and to have a zoom to see the shocks between the two particles that take place in a time scale of picoseconds. So when studying the problem in longer time scales, Einstein and Smoluchowski found that the probability distribution that characterizes theoretically the problem is a Gaussian one whose variance grows linearly with time, and it has the particularity that it's related to macroscopics because it fulfills also the diffusion equation that also states for the concentration at the macroscopic level. So going one step farther, it can be set a Newtonian equation to each particle, which is the Langevin equation that incorporates as a novelty some kind of random force that is responsible for this erratic movement of the particles. And this force is characterized because it has null mean, and its correlation is given by the fluctuation dissipation theorem. So what we study actually is this Langevin equation, but under the overdamped regime, which means that it's a low Reynolds number in which inertial terms don't play any role. So we can avoid them and have only friction, and we can eventually add some external force and some nonlinear potential in order to have new effects on the probability distribution. So that's what we do, but before trying to resolve the Langevin equation, it's advisable to take out its dimensions. So finally, we have a system in which only two parameters are left, that are the force and temperature. So then we resolve it numerically. We have many, many trajectories for many, many particles, and then we can do statistics on these trajectories. In particular, we study the mean and the variance and see what time dependence they have. But to have a problem which is not the normal one, we introduce to the equation some nonlinear potentials that in our case are fully random potentials. Fully random potentials are like these ones, and they are characterized by its correlation function. So we change the correlation functions and obtain different potentials. Also, we study the problem in 2 dimensions. So first, on 1 dimension, we analyze the different exponents that the time dependencies of the mean and the variance, and we see that we can find superdiffusion, subdiffusion, and also subtransport. When we study the probability distributions, we find probability distributions that are far from the Gaussian. In particular, we see that they are asymmetric, and we recover for higher forces the normal case in which we recover the Gaussian distribution, that is the one at the bottom. Then, for 2 dimensions, we have to separate the direction along the force and the perpendicular to the force in order to study the problem. And we have some plots about the movement of the particles. We have a cloud of particles, and see how it evolves on time. For example, this case for lower forces is a kind of subdiffusion. Then as we increase the force, we have superdiffusion, in which particles travel much far. Then we find a region in which the variance has not a steady temporal relation, and so diffusion can be set, because many particles get trapped while the others move a lot. And at the end, we recover the normal case in which the spot, the cloud of particles move at once. Finally, just remember that we work on the overdamped system in which we have no acceleration, and in the future we will work in the infradamped regime in which acceleration states. Thank you very much.